Spotlit right now?
Yeah, I can spotlight.
Yeah, I think you're spotlit right now. All right, can folks hear me? Switch, there we go. So welcome everybody to CC Colloquium for January 26, 2022. We are thrilled today to host the first ever Peter Busick New Directions in Mineralogy and Petrology lecturer, Professor Catherine Cam Macris. So a proper introduction in just a minute by Tom Sharp. Before that, just a couple quick announcements. So Virtual Night Sky is tonight at 7 p.m. Craig Hardgrove will be visiting. You can get more information about that on the CC website, or I think that Kim may put a link to that in the chat. Also, community conversation tomorrow with Minnie and the CC leadership. And I'll be interviewing ASU Professor Ephraim Lim about the evolution of viruses, and he's going to help us understand where the pandemic may be going. So that should be fun. And with that, unless there's any other announcement that I've missed, I am thrilled to turn this over to Tom to introduce our speaker.
Thanks, Ariel. Yeah, it's my great pleasure to introduce Cam Macris today. She's from the Department of Earth Sciences at Indiana University, Purdue University, Indianapolis. And we asked her about this. So Indiana University and Purdue had satellite campuses in Indianapolis that were merged in 1969. So that's the origin of the name. She is the MSA Distinguished Lecturer. Specifically, she is the very first Peter Busick New Directions in Mineralogy and Petrology lecturer. Cam got her Bachelor's of Science in Geology at Louisiana State University in 2002. She did her graduate work, a master's and PhD at UCLA, earning the PhD in 2012. And then she postdoced at Caltech. She took a faculty job at the Indiana University, Purdue University campus in 2015, and where she has remained. She's a mineralogist, a geochemist. She works in some fascinating areas, including metamorphic petrology, isotope geochemistry, and high temperature processes associated with impacts. And that's what she's going to tell us about today. I noticed from her CV that Cam is also very involved in issues of inclusion, diversity, and equity, when she's participated in lots of professional development activities in this area. So she would fit right in with us here at CC, since this is very important to us as well. With that, let me introduce the Mineralogical Society of America Peter Busick lecturer, Cam Macris, who will share her talk entitled Seconds After Impact, Insights from Impact Processes from Ultra-High Temperature Experiments.
Thank you so much, Thomas, for that great introduction, and thanks, Ariel, also. I'm very excited to be talking to you all today about my research and to be giving your first seminar of the semester, and especially honored to be speaking as the first Peter Busick New Directions in Mineralogy and Petrology lecturer in an audience where Peter Busick is present. So I'm very excited about this. And I am going to go ahead and share my screen now so I can begin. So bear with me for 1 second. Okay, can anybody confirm, maybe with a thumbs up, that you are seeing my slide and only my slide?
Looks good.
Thumbs up.
Great, okay. So the title of my talk, already shared, is Seconds After Impact, Insights into Impact Processes from Ultra-High Temperature Experiments. I thought I would start just by sharing a little bit about me, because I'm not able to be there to visit with you all, unfortunately. I was planning on coming, and then because of Omicron, that plan got changed. And I'm pretty bummed about it, to be honest with you. I wish that I was able to chat with people and get to know you all. But I thought I'd just start out and share a little bit about me as if, as we're getting to know each other. So my name is Catherine Macris. My initials are Cam, but everybody calls me Cam. So please feel free to call me Cam. My pronouns are she, her, hers. I'm a first-generation college student, a federal aid recipient. I was publicly educated K through 12, and I'm the first and only graduate student in my family. The picture I'm showing here is last summer with my, a PhD student in my group who is now Dr. Wiguang Pan. This was his commencement, and it was a very proud day for me and my group. I'm also a dog mom. I took this picture this morning. It was 2 degrees in Indianapolis, and my dogs were on their heated bed, being very cute. I'm also very passionate about science communication. I'm very excited to be able to share that passion with you today. And also, I believe very strongly that earth sciences should be welcoming and accessible to everyone. So I'll go ahead and get started. Let's get to the talk. So this is a cute little GIF from NASA showing the basics of impact processes. So here we go. So what we saw is that a meteoroid or some other space rock was traveling at hypervelocity and struck the surface of this rocky body. It ejected material from the site of impact and excavated a crater. So basically a space rock hit a planet and left a hole in the ground. Evidence of impacts can be seen in the rocky bodies in our solar system. If we look at Earth, the Moon, Mercury, Mars, Venus, we can see on these images craters. If you look up in the sky on a clear night, you can see the craters on the Moon. Here on Earth, this view of Earth, we're not seeing any craters, and we'll talk about why that is. So there are currently about 190 documented impact craters on Earth versus thousands or tens of thousands on the Moon. So the red dots here on the map of Earth and on the Moon are showing the documented impact craters. So why so few? Well, some craters are pretty easy to find. So you all are probably familiar with this crater, I'm thinking. This, of course, is Meteor Crater, also known as Barringer Crater in Arizona. So this is a massive hole in the ground. I'm sure you've all seen it. It's hard to miss. But other craters can be harder to find. So here's an example. This is showing the location of the Chicxulub crater in the Yucatan, which is buried under sediment and water. And so there are a lot of reasons why we might not be finding all of the craters that exist or once existed. We have plate tectonics, we have erosion, weathering, vegetation can destroy or hide craters from view. So let's talk a little bit about why we care. Why should we do research on impact events? Well, impacts are responsible for the formation and evolution of Earth and other planets. So as rocks in space impact each other, they accrete or grow over time, which is how planets are built from scratch. Lots of impacts kept the young Earth hot enough to differentiate, separating into a metallic core and a silicate mantle. And also, a very large impact, of course, resulted in the formation of Earth's moon. Impacts also played an important role in altering Earth's composition. So the young Earth was continually bombarded by space debris, which produced enough heat to completely melt it. And in this state, it probably lost some of its initial chemical constituents as material was vaporized by this extreme heat. So volatiles are elements or isotopes of elements that can be easily converted from liquid to gas. And this process would help to explain why Earth's composition is slightly different than meteorites. Impacts have also played a role in life on Earth. So comets and meteorites are thought to have delivered water in the form of ice and other important ingredients for life to a cooler Earth. And large impacts can also trigger mass extinctions, as in the case of the Chicxulub event that I mentioned earlier. But there are still open questions as to how impacts might cause such an extinction event. So this is actually a real book. You could buy this. I wouldn't buy it for your kid, But this dinosaur is sad because all of his friends are dead. But how? So how much of the extinction it was a direct result of the impact's immediate devastation to the local and global environment versus longer lasting after effects that we think of as being associated with large impact events. So let's shift a little bit and talk about some of the ways that we do research impact events. So luckily, large impact events aren't occurring on Earth very frequently these days. So we can't observe them directly, even though Hollywood movies would have us think otherwise. So I wanted to incorporate a little bit of participation in the talk because I know we're all tired of Zoom talks. So why don't people in the chat give how many thumbs up you thought that Don't Look Up deserved. So give your Roger Ebert score for Don't Look Up if you saw it. I think most people did see it. So another way that we research impact events is by using powerful computers to make computationally expensive models and animations, such as the one that I'm showing here. So every time the screen blinks, it's because the scale is changing. And what we're seeing is that a target struck this surface here and a crater was excavated. Also, material was melted and vaporized, and it was then ejected away from that site of impact there. So this simulation was done by Natalia Artemieva and others in a 2004 paper. It was for a 1 kilometer bolide traveling at 20 kilometers per second that struck the surface at an angle of 30 degrees. We learn a lot from these types of simulations. They take a lot of computer power and time too, and that they tend to keep them pretty short. So you see this ended at about a little over 4 seconds. So we're leaving a lot of the process here unexplored. Another way that we can research impacts is by studying the products left behind by ancient impacts on Earth. So these include craters, of course, and something called tectites. So I really like this artist's rendition because it shows what appears to be hot and molten material being ejected away from the site of impact. So this correlates with that molten material that we saw in that animation in the last slide. This is the stuff that eventually becomes tectites. So in this slightly more scientific cartoon, we see that as a projectile impacts Earth's surface, its kinetic energy is transferred to the crust in the form of intense heat and pressure, which results in fracturing and metamorphism of the underlying rock, as well as melting and vaporization of the impactor and the upper layers of target material. This material is immediately ejected away from the site of impact, as shown by these arrows. And then here, I've superimposed a crude visualization of the impact ejecta, which is an expanding plume of molten and vaporized rock, which we call the impact plume, or sometimes the impact vapor plume. This powerful plume is going to push aside the ambient atmosphere, allowing the melt ejecta, shown here as these sort of glowing blobs, to follow long ballistic paths while they're entrained in a hot gas, which buffers the temperature of the melt, allowing enough time for aerodynamic shaping, which is supposed to be inferred by the shapes of these little blobs here. At some later time, the plume collapses or dissipates, causing that molten material to cool mid-flight into a glass, so represented over here. This will later fall to the ground and people find them and we call them tectites. So the formation and evolution of tectites are determined by a number of factors, some of which include the size of the impactor, the velocity and angle, the composition of the target material, water content, etc. But here we're going to focus on the effect of vapor melt interactions in the impact plume. So these impact plume dynamics are the least well understood aspect of the impact process, and yet the very thing that may have the most devastating effects on the local and global environment. So we can learn about this impact plume by studying tectites which experienced it directly. As I mentioned before, there are 190 impact structures identified on Earth, but there are only 4 what we call major Tectite strewn fields around the world that are shown on this map here. The North American strewn field, the Central European strewn field, the Ivory Coast strewn field, and then the Australasian strewn field here is the largest by far, and also the youngest at just about 800,000 years old. So the 4 major Tectite strewn fields are outlined here, and also their associated impact craters are shown as black dots. And the black dot is conspicuously absent from the youngest and largest strewn field, the Australasian strewn field. Although a recent paper, or a 2019 paper by Sia and others, presented evidence that the crater may be buried beneath a volcanic field in southern Laos. So I'm showing you here a different projection of the Australasian strewn field. It's shaded now in green, with the red symbols showing Tectite locations where they've been collected. There are several different kinds of Tectites in this strewn field, different forms. So there are what we call layered Tectites, also called Muongnong Tectites. These are large chunks, like maybe the size of a loaf of bread sometimes. And these are thought to have cooled in puddles on the ground. And then we have the splash form Tectites, which are usually finger to fist sized. These cooled mid-flight and have those aerodynamic shapes. There are also microtectites, which are basically miniature splash forms. They cooled from small melt droplets, and also some of them may have recondensed from vapor. There are also what we call ablated tectites, which cooled mid-flight like splash forms, but then were ablated upon re-entry into an intact atmosphere. So if we can study key features of these glasses, it might lead to a better understanding of the impact plume and tectite formation processes. But first, we need to know how different temperatures and heating times affect tectites. And so that leads us to another way that we research impact events, which is by doing ultra-high temperature experiments. We can reproduce the extreme temperatures associated with impact melting and impact plumes in a device called an aerodynamic levitation laser furnace. On the right is a photograph of this apparatus in my lab. And on the left is a schematic of its parts and how they work together. So in this apparatus, a small spherical sample is levitated on top of a flow of gas that comes from below out of a specially shaped nozzle. It's heated from above with a CO2 laser, and the temperature is measured with a pyrometer. The action is all happening behind this welder's glass in this chamber here. And here you can see a photo of what it looks like if you were to look inside, which you would not want to do. So this is the molten spherical sample, which is levitating on top of this nozzle. We can use a variety of gases for levitation, such as those listed here. And we can even mix them to create different environments for experiments. So the gas is what allows the sample to float above the nozzle while it's being heated. So what we end up with is a levitating orb of molten rock, which is pretty cool. So for the rest of this time we have together, I'm going to share with you 2 studies that we've published so far where we use the levitation furnace to study impact processes. In the first study, we used diffusion in tectites and ultra-high temperature experiments to estimate the thermal histories of individual tectites. And in the second study, we determined the stable isotope fractionation of copper due to partial evaporation of melts in ultra-high temperature experiments. Both of these deal with the vapor melt interactions that we want to understand better in the impact plume. I'm going to talk less about study 1 and leave out a lot of details so that we can talk a little bit more about study 2, which is much more recent. But let's start with the first study, the diffusion study. Here I'm showing you a photo of an Australasian splash form tectite. It was cut into slabs. As you can see, this piece is missing here. That's this slab laid out above. And now I'm showing one of these slices or slabs magnified. This is just a transmitted light photomicrograph. And the purpose here is that we can see some of its features. The majority of this glass is sort of beige brown in color. it has a roughly rhyolitic composition, as you can see on this plot of alkalis versus silica. So this is the rhyolite field, here's obsidian, and here our Tectites plot. You can also see that the Tectites are more depleted in alkalis than obsidian. So something I want to point out is that entrained in the matrix glass, this rhyolitic felsic matrix glass, we see some local heterogeneities. So first I want to point out these little tiny blebs that are speckling the surface. These are almost pure silica glass or SiO2 glass, and they're called Le Chatelierite. And at the end of this talk, everybody's going to have to pronounce it. Just kidding. What these are relict quartz grains. So these used to be quartz grains. They were melted by the heat of the impact, but they did not fully homogenize with the rest of the melts. So now they're silica glass. And then these flow bands here are called Schlieren, and they're intermediate in composition between the pure silica glass and the rhyolitic felsic glass. So I'm showing you now some backscattered electron images taken on a scanning electron microscope of Le Chatelierite in that one Tectite that I was showing a minute ago. So what we can see, so all of these scale bars are 100 microns. So what we notice is that they vary in terms of their size, their shape, and their degree of vesiculation. So just to be clear, the dark gray areas are the Le Chatelierite, and then they're surrounded by this lighter gray felsic glass. So what they all do display, though, is what appears to be a diffusion halo at the inclusion host glass contact. This appears as intermediate in grayscale between the Le Chatelierite and the matrix glass, and is indicated here by these green arrows to point it out for you. So what this tells us is that silica was diffusing away from the Le Chatelierite into the felsic melt while that sample was molten at high temperature, and that the melt was then quenched to a glass before it could fully diffuse and mix in. So these images are like snapshots in time, and we could potentially extract information about the thermal history of the sample using these compositional gradients. Let's just take a second to briefly talk about diffusion so that we're all on the same page before I go any further. So in the cartoon on the left at the top panel shows two distinct compositions with a sharp boundary between them at time equals 0. At some later time, we see that the particles migrate from places where their concentration is high to places where their concentration is low. And in the bottom panel, at some much later time, the particles have reached equilibrium and are totally mixed and homogenized. So these cartoons next to them are showing the same concept in the context of pure silica melt diffusing into the surrounding felsic melt, as in our Tectites. So you've got your quartz grain that is just melted, and then the silica starts to diffuse away, and then much later you would have just a fully homogenized melt. This behavior is dictated by Fick's first law of diffusion, which states that diffusing mass transport depends on the component's concentration gradients, here, del C, and its diffusivity or diffusion coefficient, this D here. The diffusivity or diffusion coefficient is a measure of the mobility of a component, and it will vary with temperature, pressure, and composition. So now we're going to look at some data from this Tectite. So what I'm showing here is a weight percent oxide on the y-axis versus distance on the x-axis, distance as we move from A to B across this Le Chatelierite. So we're moving from the matrix glass inside the inclusion and then back out the other side. And what we see here are these compositional gradients that for silica increases from about 75 weight percent in the matrix to about 100 weight percent inside of the inclusion, and then back out the other side. And then the inverse for aluminum in red here, aluminum has about 14 weight percent, but it drops to about 0 inside of the Le Chatelierite. And then here I've just zoomed in, this scale has changed on the y-axis just to show you that all of these oxides are showing diffusion behavior. So we have multi-component diffusion happening here. How can we use this observed multi-component diffusion between the Le Chatelierite and the surrounding felsic melt to estimate the thermal histories of Tectites? Well, the answer is that we would compare it with diffusion experiments at known temperatures and times so that we could determine those diffusivities or those diffusion coefficients. And so that's what we did. We did some experiments in the aerodynamic levitation laser furnace. We wanted to replicate the diffusion profiles seen in the natural samples and use them to determine the diffusivities. We started with a powdered natural Tectite where we added in some small quartz grains. We heated these samples to temperatures between 1800 and 2400 degrees Celsius from 1 second to a couple of minutes. And the levitation gas was an ultra high purity argon gas. And what you're seeing here is the sample is fully molten at this point. And in just a second, it should quench. Let's see if we can be patient and wait for that. Here we go. We turn the power off to the laser and it's now cooled. It's a glass again. So it happens very quickly. What I'm showing here are some more backscattered electron images of cross sections of these glass spheres after an experiment. So these were heated to 2200 degrees Celsius for varying times. And there's a clear textural evolution with time. So if we start by looking at this one, which was heated for 5 seconds, some of the quartz grains, which are the darker brown, darker gray blebs, are still in the process of converting to Le Chatelierite. So we still have some crystalline quartz here. At 10 seconds, we have complete conversion from quartz to Le Chatelierite. We're also developing more and larger vesicles. By 50 seconds, we've reproduced the Schlieren that we saw in the natural sample. And in the longest experiment, we have we're nearly vesicle free, and we have significantly fewer Le Chatelierite. So we used the compositional profiles taken from these experiments to determine the diffusivities at known conditions, and then compared with diffusion profiles in the natural Tectites to determine thermal histories. And what I'm showing here are the diffusivities that we determined. So these are Arrhenius diagrams where the y-axis is the natural log of the diffusivity versus the reciprocal of temperature in Kelvin down here, and then in Celsius at the top here. And so all of the components are obeying the Arrhenius relationship. So this is the plot for silica, for Al2O3, FeO, and they all fall in a line when plotted this way, which means that we are the behavior that we're observing is definitely diffusively controlled. And then here in the lower right, I've plotted all of these lines on top of each other or on the same plot. And what you can see is that they are overlapping. They're very closely spaced, these lines. And that means that all of these components have very similar diffusivities, and as it also turns out, activation energies, which makes finding a unique solution to a given Tectite's thermal history impossible. But what we can do is we can use this diffusion behavior in experiments to come up with a family of possible thermal histories for a sample, which is what is shown in this figure here. So each of these curves is plotting the diffusivities for one of these oxides, and they all lie on top of each other as we expect based on what I just showed you. And what we can glean from this is that this particular Tectite that I showed you earlier could have been buffered at high temperatures in an impact plume for about 3 seconds if it was at 2400 degrees Celsius. For about 30 seconds if it was at 2200 degrees Celsius, and then for a little over a minute at 2000, and much longer times if it was at 1800. These much longer times are really not realistic based on expectations of velocity and trajectory of these Tectites. So we wanted to apply our work to diffusion in more samples from this strewn field. So what I showed you was just an example of data from one particular tektite. But we have curated samples of Australasian tektites from known collection locations. And we have some of the layered or Mongnong tectites, we have some of the splash form tectites, and also some of the microtectites. So far, we have measured diffusion profiles in some of the layered tectites, which are all collected in Thailand, Vietnam, and Cambodia. And then some splash form tectites that were collected in various locations in the Philippines, over here in Indochina, as well as all the way in Australia. And then here are the results of the estimated family of possible thermal histories for this large group of samples that we have analyzed. So the green curve here represents the Muang-Nong tectites, or those layered tectites. So what we can take away from this is that the layered tectites were heated at a high temperature for a relatively brief period of time. So we think they exited that hot vapor plume first, allowing them to puddle and cool on the ground. Whereas the splash form tectites, whether they landed in the Philippines or whether they landed somewhere in Indochina or all the way in Australia, they all experience similar thermal histories. So we interpret that right now as that they were entrained in that hot plume for longer times than the layered tectites, but they were all in that plume for a similar amount of time, and that their ultimate thermal histories are uncorrelated with the distance traveled, which is a surprising result. So here's just another way to show this information to summarize these results so far. We found that the layered tektites experience temperatures between 2000 and 2200 degrees Celsius for very short periods of time, just a couple of seconds, whereas the splash form tektites were heated to those high temperatures for longer, so between 20 and 50 seconds. And the interesting thing, again, is that statistically, all of the splash forms experience the same thermal history, no matter where they were collected, which is surprising, as we expected that the sample's heating history would vary from location to location. So if we look back at this final shot of Artemieva's hydrocode model, our results offer possible temperature time pass for this yellow molten future tektite material here. We can now envision what might happen to this tektite parent material if the model was run for much longer times. So some of the melt would fall to the ground first, cooling before cooling to form those layered or Muang-Nong tektites. The rest of it would continue to travel away from the crater, entrained in the hot vapor, which is going to buffer their melt temperatures for longer, until at some later time the plume dissipates and those airborne melt particles cool very quickly and continue along their ballistic pathways to their final location. So to summarize this first study, laser heating experiments successfully reproduced diffusion profiles between Le Chatelierite and felsic glass observed in tektites. The layered tektites were heated for shorter times. We think they exited the plume first and cooled in puddles. The splash form tektites were buffered at high temperatures for relatively longer periods of time. They exited the plume later, then cooled quickly, continuing along their ballistic paths until landing. And we still need to measure profiles in ablated tektites and microtectites to more fully understand the impact plume. But the temperature time estimates we have so far can guide future experiments that investigate tektite formation and evolution. And that brings me to the second study that I'm going to tell you about. This is the study where we're looking at stable isotope fractionation due to partial vaporization of melts. And this is that map that I showed you earlier of the different tektite strewn fields. And then on the right, I'm showing you a stacked bar chart that shows the relative average major oxide abundances for tektites from each strewn field. These show that tektites have roughly similar compositions in general, with some interstrewn field variations. But if we consider the average composition of all impact melt rocks and glasses combined and compare it to continental crust, we find that their compositions look very similar. In fact, a lot of work has been done in the past to try and identify the source material of Tectites. Overwhelmingly, the geochemical evidence indicates that Tectites formed by the melting of terrestrial upper crustal sediments. This idea is supported by the major and trace element geochemistry, including rare earth elements. In this plot on the top is from Howard 2011, which shows how closely Australasian Tectites match the trace element pattern of shale. And then down here is a similar plot showing good agreement between Tectites and Chinese loess. So while there's some argument about the exact flavor of sedimentary material, that it was the protolith for those Australasian Tectites, there's overwhelming evidence that they were upper crustal sediments. Also, radiogenic and stable isotope data have been crucial in definitively linking Tectites to upper crustal sediments, especially beryllium-10. But if we look at an overview of stable isotope fractionation behavior in Tectites, it's not really straightforward at first glance. So on the left here, we see a list of isotope systems that appear to be unfractionated in Tectites relative to their protoliths or parent materials. In the middle are systems that are higher, including copper and zinc. And then on the right, we have oxygen, which is lower in Tectites than it is in the proposed parent material. These lists do not include data from microtectites, for which there is limited data that indicates that there's both heavy, light, and unfractionated samples for potassium and iron. But that's a whole different story for a whole different talk. So we're going to leave that for now. And for this story, we're going to focus on copper and zinc isotope fractionation in the larger Tectites and how recent experiments from my lab and another lab at IGPP in Paris contribute to our understanding of this behavior in high temperature melts. So turns out most Tectites are about 4 to 6 per mil higher in delta 65 copper than their proposed parent materials. So this histogram here is showing the range of variability in all igneous rocks and clastic sediments as relative frequencies that are both hovering at about 0.08 per mil, which agrees well with that of the bulk silicate earth, which is plotted as this gray bar on the plot on the right, showing the delta 65 copper variability in chondrites and Tectites. We can see in this plot that Tectites range from about 2 up to about 12 per mil, although most are around 4 to 6 per mil. And they are certainly higher than their parent materials, which would be represented by the bulk silicate earth here. So if we look at the same data for zinc, we see that sediments are around 0.28 per mil in delta 66 zinc, which is again represented over here in this plot as the gray bar as bulk silicate earth. And we can see that Tectites range from about 1 to 4 per mil, and that they are about 1 to 2 per mil higher in delta 66 zinc than sediments or the protolith. So some possible mechanisms that have been proposed for altering stable isotope ratios of Tectite parent material include mixing between source material, which we're going to assume are these upper crustal sediments, and then some isotopically different component. It's also been suggested that maybe there was secondary alteration. And because we know Tectites experience extreme temperatures in the impact plume for seconds to minutes, it seems likely that they could have fractionated due to partial vaporization. In reality, it's probably some combination of the above, and we could quantify the contribution of each experimentally. And in my lab, what I can try to tackle is the vaporization aspect. So fractionation due to vaporization at high temperatures would lead to a negative correlation between isotope values and concentration. And that is because the light isotopes are going to be preferentially lost from the melt as material is vaporized. So in other words, the elemental concentration goes down, and simultaneously the isotope value goes up as the heavier isotopes get concentrated in that depleted residue. And for copper, we see that this generally appears to be the case. As copper concentration decreases, moving from left to right here, the delta 65 copper gets higher. This beige bar on the bottom represents the bulk silicate earth, and you'll see that these Muongnong or layered tectites are unfractionated relative to bulk silicate earth. And the plot on the right is the same data, but the y-axis scale has changed. And I've added here curves representing the theoretical predictions of fractionation according to Rayleigh evaporation models for pure copper, copper oxide, and copper sulfide, which you can see do not explain the Tectite data. We can look at the same relationships for zinc here and see that there is also a general trend of increasing delta 66 zinc with decreasing zinc concentrations. And again, a theoretical Rayleigh fractionation curve for zinc evaporation does not explain the Tectite data. So much like the first study I presented, I wanted to try and see what conditions could replicate the observations from the natural samples. So we did vaporization experiments using a synthetic basalt glass doped with extra copper as the starting material and heated these spheres in the levitation furnace for seconds to minutes at high temperature using argon gas. The video shows the melt being partially vaporized, which results in light isotopes and volatiles being preferentially lost to the vapor. And now let's look at the results of these experiments. We see in this plot of copper concentration versus experimental duration that the highly volatile copper is lost quickly at these temperatures, and that longer duration experiments had copper concentrations actually below detection limits. Here we see that the delta 65 copper of those experimental residues, or the glasses left behind after the heating, increases as the copper concentration decreases, just as we said it should. In this plot on the right, I've plotted the same data as the plot on the left, but the axes are now different. So here I'm plotting it as the natural log of the isotope ratio, the 65-63 copper ratio in the experimental residue over the copper isotope ratio in the starting material. And then the x-axis is the negative natural log of the fraction of copper remaining. And here we get a very strong linear relationship defined by all of the experimental data. But why would we do this? Well, if we look at the equation for Rayleigh evaporation shown here, which describes the partitioning of isotopes between two reservoirs as one reservoir decreases in size. So here, R is the ratio of copper isotopes in the residual melt. This is what we measure in our experiments after heating. And this is over the initial ratio. And this is what we measure in our starting materials. F is the fraction of copper remaining in those experimental glasses. And then alpha here is the fractionation factor. And that's what we want to know. So we can see also from this side of the equation that the fraction of copper remaining is simply the concentration of copper in the experimental residue divided by the starting material. If we take the natural log of both sides of this equation, we can get rid of that exponent. And now we have the relationship as the equation for a line, where the alpha, or the fractionation factor, is now embedded in the slope of this line. And so that's how we determine that we got an experimental alpha of 0.996 here. So now I'm showing you again copper concentration on the x-axis versus delta 65 copper on the y-axis. You've seen all of these data before, I'm just comparing them. So now the experimental data is represented by this orange curve. The red circles are natural Tectite data. And then these curves here are those theoretically predicted Rayleigh fractionation curves. And then on the right, I'm presenting the exact same data, but again, I've manipulated these axes. So now the x-axis is the natural log of that fraction of copper remaining. And here, these are the theoretical lines that are these lines over here. Here are our experimental data, and then here are the natural tektite data. Another line here is this dashed orange line. And what this represents is how that experimental line would shift its y-intercept if we plotted it using a different value as the starting concentration of copper. So in the dashed orange line, we use the concentration of copper that we find in those Muongnong tektites as the initial copper concentration, instead of the value that is estimated for the bulk silicate earth, which is what is used for this solid orange line here. But either way we plot it, the experimental trend comes closer to the actual tektite data than these curves for simple Rayleigh evaporation of ideal species. But we still see an offset between the experiments and the natural samples. So what can account for these differences among these trends? So this is the same plot as before. I've just labeled these different areas so that we can keep track a little bit easier. So let's start by discussing some of the possible reasons for the difference between the experiments and the natural data versus these theoretical fractionation lines. So why are these the steepest lines here? One idea is that there could be a diffusion limitation that is suppressing fractionation in the experiments and the natural samples. So in other words, if diffusion of copper from the interior of the melt to the surface can't keep up with the evaporative flux at the surface, what we could see is that there would be less fractionation. However, in a 2019 paper by Jiang and colleagues, they did in situ measurements of zinc and copper on a tektite cross-section, shown here, and they observed no systematic differences or zoning within analytical error. So these data do not support the idea of diffusion-limited fractionation. Also, the rate of copper loss from the melt is not consistent with diffusion-limited fractionation. So this is the same figure you've seen before, where it doesn't take long before you start to lose so much copper you can't even detect it. So another culprit for the offset between the experimental and theoretical alphas could be the role of return flux in our experiments. So in this photo on the left, we see a sample being heated. On the right, we see that the vapor phase is surrounding that molten sphere, leaving a turbulent wake as it travels. And what this tells us is that the vaporized material is interacting with the melt, and that some of that evaporated particles are likely recondensing onto and into the melt. So this phenomenon would lead to a larger alpha than what is theoretically predicted, which means less isotope fractionation. If we also try to think about what might be behind the difference between our experimental alpha and the natural tektites, so what's up with the difference between these two trends here, we're going to immediately consider that we are imperfectly replicating the tektite formation process. So firstly, the melt composition in our experiments is more mafic than tektites. Secondly, we are likely not replicating the FO2 of an impact plume with the argon gas as our atmosphere. And then also, the vapor pressure surrounding a molten tektite in an impact plume is likely higher than that in our experiments. Also, the gas flowing around a tektite in nature, in an impact plume, is likely interacting differently than the gas, our levitation gas, flowing around our molten samples. So higher vapor pressures would suppress fractionation, and that makes sense looking at the data here. So the vapor pressure and that return flux are related to each other. So let's take a minute to talk about how they're related and how they affect the fractionation. So here is, I'm showing you a spectrum of evaporation behaviors. So on one end, this end over here, you've got what we call ideal or free evaporation. This is where all evaporated particles are quantitatively removed from the melt such that no recondensation is occurring. So this would be the case for evaporation in a vacuum. And if this was happening in our experiments, it might look like this cartoon that I have that I've created here, where all of the evaporated particles are immediately carried away in the gas flow and none of them recondense. On the other end of this spectrum, you've got a situation where you have equilibrium between the gas and the vapor, meaning that the evaporation and condensation rates are constant. And this would exist in a closed system where you don't have material escaping. Our experiments are in the middle here, somewhere in the middle of these two end members, as shown in this middle cartoon. And what we see here is that there is a return flux where some of the evaporated particles are returned to the melt and recondense, while some are carried away. And then in this scenario, the evaporation and condensation rates are not constant. So in the free or ideal evaporation scenario, what we have is a purely kinetic isotope fractionation, which is going to be larger than the fractionation due to partial evaporation, as we see in our experiments, which in turn is going to be larger than the fractionation that we would expect at equilibrium conditions. These different degrees of fractionation and rates of evaporation versus condensation are going to be dependent, at least in part, on the partial pressure of the evaporated particles at the surface of the melt. In our purely kinetic case, the partial pressure is going to be 0, which is lower than the partial pressure in our experiments, which is lower than the partial pressure at equilibrium, which would be saturation. And the fact that we have some return flux in our experiments means that the partial pressure is greater than 0, and thus the fractionation will be suppressed relative to the purely kinetic case. So if we revisit this figure now, I think we can be more convinced that the return flux and the partial pressure at the surface of the melt are likely playing a role in these differences. The way that the gas is interacting with the melt is having an effect on the isotope fractionation here. So the theoretically derived alphas would be relevant for free evaporation in a vacuum, leading to the highest fractionation. And while we don't know the exact partial pressure of evaporated species at the surface of the melt in either our experiments and in the molten tectites, it would make sense that the vapor pressure in an impact plume would be higher than that induced by the gas flowing in the levitation furnace. And this matches the data here where we see that our levitation experiments are more fractionated than tectites. So earlier I told you about zinc and then I stopped talking about it. So let's bring it back and let's compare the experiments that have been done for copper and zinc. So there was a study in 2019 by Wimpenny et al. And they did similar experiments to mine in a laser levitation furnace to study zinc isotope fractionation due to evaporation during atomic bomb tests and tektite formation. They used two different starting materials. They used an arcosic soil and a rhyolitic soil. And here those experiments are plotted together also with tectites shown as these green symbols here. And also the trinitite, nuclear testing fallout glass. And you can see that all appear to fractionate zinc isotopes with progressive zinc loss, just as we saw for copper. So here we're comparing directly the copper and zinc results from these experiments. So on the left, we're comparing the evaporative loss of copper, of copper in orange, versus zinc, which is in gray here. And what we see here is that copper is considerably more volatile. This line is way more steep than zinc at the same temperature. And then on the right, we're comparing the isotope fractionation between copper and zinc in these experiments. And we see similarly that copper, which is now shown in red over here, is more fractionated at similar temperatures than zinc, again shown in gray. Both systems showed a lack of temperature dependence at these high temperatures for the fractionation factors. It's worthy of pointing out. So on the left here, now we're still looking at the volatility of copper and zinc, but now in natural samples. So this is a plot of the relative enrichment and depletion of elements in Tectites versus Chinese loess, which some think is the protolith of Tectites. And what we see is that copper is much more depleted and therefore is more volatile than zinc. Over here on the right are the plots I showed earlier of copper and zinc isotope fractionation relative to bulk silicate earth. This time zinc is on top and copper is on the bottom. And this also agrees with our experiments in that copper is more fractionated than zinc in these Tectites. What I'd like to point out, just a last thing, is that in the upper right-hand corner of these plots, the authors provided the half condensation temperatures for these elements. So as geochemists, we regularly look to the half condensation temperatures of elements as an easy predictor of volatility, with lower temperatures indicating higher volatility. And that is in fact the exact opposite of what we observe here. So all of this data tells us that this practice of using half condensation temperatures as a guide for relative volatilities of elements may not be valid for all materials. These temperatures are calculated, these half condensation temperatures, for condensation in a hydrogen-rich solar nebula gas at very low pressures. And they are likely not applicable to Tectite formation in Earth's atmosphere. So one last figure. Here I'm showing a figure from Jiang et al. 2009, where they used magma code to do thermochemical calculations at conditions that are relative to Tectite formation. They used loess as a starting composition, and they made this plot showing the composition of a residual melt after being heated to 1500 Kelvin as a function of the total fraction vaporized. This is on a log scale. What we see here, or the takeaway, is that copper is lost before zinc and is therefore more volatile at Tectite forming conditions, which is contrary to those predictions based on the half condensation temperatures. So I will summarize this second study. Most Tectites have high delta 65 copper relative to their proposed protolith. Vaporization experiments show that evaporation residues are enriched, that the preferential evaporation of light isotopes due to vaporization leads to a higher delta 65 copper. The delta 65 copper of Tectites and experiments are not fully explained by a pure kinetic evaporation model. The effect of return flux and saturation due to gas flow is an important factor in the isotope fractionation. Copper is more volatile than zinc at Tectite forming conditions, which is contrary to expectations based on condensation temperatures. And copper isotope fractionation is larger than that of zinc. And lastly, I would like to just plug a study that we hopefully will have coming out soon. It is in second stages of review, where we look at iron and magnesium fractionation in chondritic melts, also in levitation experiments. And what we see is that the fractionation, again, is highly dependent on the interaction between the melt and the flowing gas. And in fact, in this paper, what we do is we say that stable isotope fractionation between melt and vapor can be used as a velocimeter. Velocimeter. I don't know how you say that word. Maybe we can discuss afterwards. So I'd like to end by thanking all of my collaborators shown here from various institutions, also all of the funding agencies that supported this work. And lastly, I would like to thank the Mineralogical Society of America And specifically, I would like to thank Peter Busek for supporting the Peter Busek New Directions in Mineralogy and Petrology lecture. It is my absolute honor to be able to give this talk in his audience, and I'm very happy to take any questions that you have now. And then here's just a plug for some MSA publications, and I'll leave that up there. But I will also stop sharing my screen.
Great. Thank you very much for that talk. That was, as a fellow isotope geochemist who deals with non-traditional isotopes, that was one of the clearer explications of some of this stuff that I've seen in a long time. So thank you.
Oh, great. If you don't mind, I'm just going to turn my light on. The sun has set since
I noticed as you were talking, the sun was setting. So we can tell you're east of us. So folks who have questions, please put them in the Q&A and or feel free to raise your hand. I see Peter's raised his hand. I'm going to allow Peter to talk. Oh, where did he go?
I promoted him to panelist.
Okay, great. So Kim has just promoted you to panelist, Peter. So please feel free to speak up.
Cam, wonderful talk. Thank you so much for the nice shout out on it. It was very interesting and a big pleasure to hear it. You discussed extremely interesting results based on unusual experiments. Maybe you can tell us a little bit about the levitation experiments, the experimental variables, and how those might affect your results.
Sure. So there are a lot of variables when it comes to doing these experiments. And another thing that I've learned, so my background from my PhD was I was doing a lot of experiments looking at equilibrium fractionation. And when you're dealing with kinetic processes, things get a lot messier. And so that's one of the complicating factors of doing these kinds of experiments. But some of the different variables that go into the experiments that we can try to control for, one is the size of the sphere that you're starting with. So that's going to affect the cooling rate. And also, if you are dealing with something where you expect a diffusion limitation, then the size of your sphere will also affect the end result because of the distance that the component would have to diffuse to get to the surface. So one thing that we do try to control for as much as possible is that to keep the size of those starting spheres consistent. And another thing that we try to control for is the rate of gas flow that is being used to do the levitation in the experiments. In the beginning, we really didn't think about it that much. It didn't occur to me that that would be important, to be honest with you. We would just use the gas flow that would produce a stable levitation. And what we ended up learning is that it actually can have an effect depending on what kind of experiment you're doing and what your end goal is. But when it comes to isotope fractionation, it turns out what we have learned, what we are still learning, is that the interaction of that flowing gas around the melt definitely has an effect on the isotope fractionation. And so we try to control for size of the sphere. We try to control for the same gas flow rate. We also, the way that we do the experiments is that we use a computer program to tell it to heat at a certain rate, to hold it at a hold temperature for a certain amount of time, and then to cool it either at some controlled rate or to just turn off the power to the laser and have it cool immediately. Usually for these kinds of experiments, we're doing the latter. We're just telling it to cool immediately. But those things also we can control for. So we can have them heated at the same rate for each experiment, and we can have them to be held for a specific amount of time and then cooled the same way. And let me see, what else am I not thinking about? So for some experiments, depending on the starting material, you could have so much volatilization happening that it's like literally boiling. And so sometimes that can affect things. Sometimes the melt can become unstable because so much is happening to it. It's bubbling and bubbles are popping at the surface. And so in some cases, it might sort of fall out of the gas stream. And if it hits the nozzle and you're doing something like these isotope fractionation experiments, then you just can't use that experiment anymore. It's tainted. And so there's a lot of, we try to be very careful about that, making sure that when it's molten, it never touches the nozzle. And yeah, I think those are the things I can think of right now that we do try to control for it. Did you think of anything that we should be controlling for that I haven't thought of?
No, I have a last question and then I'll turn it over. Is how do you determine the size of the sample that you use and how do you insert it into the flow?
Oh, that's a great question. So we determine the size of the sample because we use, so usually what we're starting with is a powdered material as the basic starting material. And what we do is we fuse that powder with a defocused laser at just above its melting temperature so that it forms a sphere. And the way that we do that is controlled and consistent. And so if we use the same amount of powder to start and we fuse it with the same conditions, we can usually produce spheres that are fairly similar in size. And then the way that we introduce it to the nozzle and to the gas flow is that I have it's called a vacuum chuck. And it's basically just a long tool that is sucking air. And at the end of it is a diameter of about 0.5 millimeter. So if I touch it to the sphere, it'll pick it up. And then I carefully put it inside the chamber and I let it go. And I hope that it doesn't fly out.
Great. So in the interest of time, we're running a little long. I think those who feel they need to go somewhere else should feel free to do so. But if you're willing to stick around, there are a few other, a couple of little questions that look pretty nice that we might want to answer. If you're willing to stay just a few minutes longer.
Oh, yeah, I'm happy to stay as long as people want to chat.
Great. So those who feel that you need to leave, please don't be bashful doing so. But thank you, Cam, just before everybody goes, those people go, for really a lovely talk, describing some really cool, elegant experiments. So questions that are here, I mean, they're nice basic questions like, how are the Tectites in the South Indian Ocean retrieved?
The micro Tectites in the ocean? Are those the ones?
I guess, yeah.
Oh,
Yeah.
so yeah, if you're looking at that map of Tectite collection locations, the ones that are collected from the middle of the ocean, they're always micro Tectites. Well, I mean, I'd say almost always. And they're collected from sea cores, from ships.
Right, so there's sediment cores at the bottom of the ocean, right?
Yes. Mm-hmm.
Yep. Are Tectites the same as impact melt rocks? So a little nuance.
So yes and no. There's a lot of, geologists, we like to name things, and then some people like to name them in one way and some people like to name them in a different way. So there are some inconsistencies in the community with how we talk about these things, but the way I define a Tectite, it is an impact melt glass. So if you want to call that a rock, you could. But specifically, Tectites are impact melt glasses that have traveled a distance of at least 8 crater diameters away from the site of impact. So they're distal impact ejecta as opposed to proximal, or the ejecta that is in and around, immediately around the crater.
Great. Somebody asked, can you recommend a place to learn more about the levitation experiments and see some videos?
Yeah, well, actually, my lab was featured on an episode on a show that was on the Science Channel a couple of years ago, and they took a lot of video of the apparatus and in us using it. And the name of the episode, so the show was called Space's Deepest Secrets. That's the name of the show. And then the episode we were on was called The Violent History of the Moon or something like that. I can send a link to it. If you guys want to watch, if y'all want to watch, I'll send a link and you can send it out.
If you do, I'll pass it around.
Okay.
Send the link to me and
Okay.
I'll distribute it.
I will do.
Let's see, other questions. How do you collect tectites, just in general, I guess? Depends.
Yes, so that's a great question. Usually, tectites are usually collected, if they're not from a deep sea core, they're usually actually collected by locals in the areas that around the Australasian, if we're talking specifically about the Australasian strewn field, and then those locals sell them. So it's actually hard to find samples where you know exactly where they were collected, because not that many samples in circulation have that kind of provenance that you can really trust. So it was actually hard to curate a collection of samples where I could really trust the location data. And I was gifted those by Billy Glass very generously, and also borrowed some from the Smithsonian. And so then those were collected by researchers, who were very specifically and carefully documenting where they were found.
Okay, and I guess the last question, unless somebody else has something, how can you determine whether two tektites come from the same impact event?
Good question. So their geochemistries will have some differences. So you can use geochemistry, and also if you can date them. So one way that these are dated is with fission track dating. And if you can date a tektite, then you can pretty confidently say which tektite stream field it came from. Oh, somebody found the...
Yep, I just put it in the chat. So we have the link to the TV show, or at least to the Internet Movie Database description of it, which may have links in it. So,
I found it too.
all right, Kim's already found it. So we'll get it to you, Peter. You could circulate it to your students. All right. So unless there's any further questions,
I've got a couple questions.
Tom's got questions. All right,
So-
go for it.
Why are Moldavites, the Eastern European ones, so different looking than all the others?
Oh, good question. So Moldavites, where's my Moldavite? It's at home. What Thomas is referring to is most tektites are sort of brown, gray, black looking when you're looking at a hand sample of one. And Moldavites are a really beautiful green color. And it's the iron in Moldavites is more reduced than the iron in the other tektites, such that you're having more 2+ than 3+, and that's what's giving it that green color.
They also have very different textures.
Yeah, they do. They're less sort of they're less aerodynamically shaped. It's more kind of like friable masses looking. I think that is a result of the different composition.
Yeah, so its interaction with the atmosphere was somehow different.
Yes.
Okay.
But I don't know enough about that to be able to tell you something that you probably don't already know.
One more question. So this plume of vaporized rock and melt, this is a huge amount of energy. What does it do? What does it do to the strewn field on the ground to have all of this hot material flying through the air? I mean, it must put a lot of heat both in the atmosphere and on the surface through the strewn field. Is that true?
Yeah, well, I mean, depending on the size of the impact and the amount of melt that's produced. So if you think about, for example, like the Chicxulub impact, there are a lot of spherules that were produced from the Chicxulub impact. There weren't, as far as I know, there aren't the macroscopic tektites, and my intuition is going to tell me that that's because of the location and the fact that it was impacted into what was an ocean at the time. but if you have a lot of melt, and that melt, if the impact is big enough to make that melt leave the atmosphere and then re-enter the atmosphere at some other location, like for example, those Australasian Tectites that are ablated, then you're definitely going to be heating up the atmosphere there. And as those, well, they cool again before they hit the ground. So I think you're heating up the atmosphere, but I couldn't tell you to what degree you'd heat it up. It would definitely depend on the amount of melt.
Okay.
There was a really great, have you ever listened to Radiolab, that podcast?
Yes.
There was a really great Radiolab episode called Apocalyptica that Jay
Jay
Malash, yeah. And he talks about that.
Yeah. Thank you.
All right. All right. Well, let's thank you again and for lovely talk, and look forward to somehow getting you here in person. I'd love to show you the labs and talk isotopes and all this kind of stuff. And I'm sure there's plenty of people here who would enjoy talking with you, meeting with you. So
yeah, that would be fantastic. I would love it. And I'll save that velocimetry talk for next time I come.
sounds great. Cool. So why don't we stop the recording